Chapter 7, we're going to be talking about work, energy, and energy resources. So we're switching on gears just a little bit. Some of these problems and examples, really, that we're going to go through in these chapters that are coming up are a different way to solve like problems from chapter 2, chapter 3, and so on. Because we deal with energy. Everything that we encounter on our everyday lives has energy, some type of energy. And there are times where we can actually solve for whatever energy that object has. And from there, be able to figure out a velocity, figure out an acceleration, or something like that. So we'll go ahead and get started. Energy and work. We use these words, work and energy, in everyday life, but in science and in physics especially, these correspond to special ideas. There is no simple yet accurate scientific definition for energy. Energy is characterized by its many forms, which you can no doubt name several kinds, and the fact that it is conserved. We can loosely define energy as the ability to do work, admitting that in some circumstances, not all energy is available to do work. Because of the association of energy with work, we begin this chapter with the discussion of work. Work is intimately related to energy and how energy moves from one system to another or changes forms. So, like this chapter started off saying, there are different forms of energy, and not all the times are those forms of energy transferable. Sometimes we do lose energy whenever we do transfer from one type of energy to another. And you'll see why in a second. For work, the scientific definition of work differs in some ways from its everyday meaning. Certain things we think of as hard work, such as writing an exam or or carrying a heavy load on level ground, are not work as defined by a scientist. The scientific definition of work reveals its relationship to energy. Whenever work is done, energy is transferred. For work, in the scientific sense, to be done, a force must be exerted, and there must be a motion or displacement in the direction of the force. So that gives us our work equals our absolute value of our force, cosine of our angle, if there is an angle, times the absolute value of our displacement. Um, Formally, the work done on the system by a constant force is defined to be the product of the component of the force in the direction of motion times the distance through which the force acts. For one-way motion in one dimension, this is expressed as the equation we just went through. Like I said, work is the W, displacement is the D with the vector sign on top, theta is our angle, force is our force vector, and displacement vector with D. We can also write this as W equals FD cosine theta to find the work done on a system that undergoes motion that is not one way or that is in two or three dimensions. We divide the motion in in one way, one dimensional segments, and add up the work done over each segment, just like kinematics. So we break it apart if that is the case. So here are some examples of work being done. For A, the work done by the force on this lawnmower is FD cosine theta. You see that there's a force pushing down on the lawnmower going at a displacement, and the force is at an angle. Pretty straightforward. For B, a person holding a briefcase does no work on it because there is no motion. No energy is transferred to or from the briefcase. So work is equal to zero. Our displacement is zero. So obviously, since our displacement is zero multiplied by the force, it's zero anyway. For C, the person moving with the briefcase horizontally at a constant speed does no work on it and transfers no energy to it. The reason there is no work done here, our constant speed means our acceleration is zero. Acceleration is zero, well, force is zero. Force is zero times whatever displacement is still zero. For D, work is done on this briefcase down here by carrying it up the stairs at a constant speed because there is a necessary component of force in the direction of the motion. Energy is transferred to the briefcase and could in turn be used to do work. For E, when the briefcase is lowered, energy is transferred out of the briefcase and into the electric generator. Here, the work done on the briefcase by the generator is negative, removing the energy from the briefcase because F and D are in opposite directions here, as illustrated here. F is upwards, D is downwards. For work and energy have the same units. From the definition of work, we see that those units are force times distance. Thus, in SI units, work and energy are measured in Newton meters. A Newton meter is given by the special name joule, which is a capital J. And you'll see here that 1 joule is 1 Newton per meter, or times meters, which is essentially is 1 kilogram times meter squared over second squared. 1 joule is not a large amount of energy. It will lift a small 100-gram apple a distance about 1 meter. So here we'll tackle that problem, the A example here. For example, 7.1, how much work is done on the lawnmower below if he exerts a constant force of 75 newtons at an angle of 35 below the horizontal and pushes the mower 25 meters on level ground. So we have a force, we have a displacement, and we have an angle. Plug that all in, you get 1,536 joules, or written as 1.54 times 10 to the third joules. Converting work into joules, in joules, 2 kilocalories yields. This is a direct conversion, so this is nothing that can be manipulated or found. So 1 kilocalorie is 4,184 joules. So if we were asking kilocalories, it would be 0.367 kilocalories. Some types of work leave the energy of a system constant, whereas other types change the system in some way, such as making it move. So what happens to work done on the system? Energy is transferred into the system, but in what form? Does it remain in the system or move on? The answer depends on the system. For example, if the lawnmower is pushed just hard enough to keep it going at a constant speed, then energy put into that lawnmower by the person is removed continuously by friction and eventually leaves the system in the form of heat transfer. In contrast, work done on the briefcase by the person carrying it up the stairs is stored in the briefcase earth system and can be recovered at any time by doing work later. In fact, the building of the pyramids in ancient Egypt is an example of storing energy in a system by doing work on the system. Some of the energy imparted to the stone blocks is in lifting them during the construction of the pyramids remains in the stone earth system and has the potential to do work. So it really just depends on what the scenario is for it to lose energy. The more constant one that you'll see is heat transfer. If there's any heat being produced, that'll go into the environment and the environment around whatever object is being heated, and that's going to be a loss of energy there. We know from the study of Newton's laws that net force causes acceleration. We can see that work done by the net force gives a system energy of motion, and we can find an expression for energy of motion. Let us start by considering the total or net work done on the system. Net work is defined to be the sum of work done by the external forces. That is, net work is the work done by the net external force F net. In equation form, it would give you W net, net work, equals net force, D cosine theta, where obviously theta is the angle between the force vector and displacement vector. So for A here, we have a graph that is F cosine theta in the y component and D in the x component. When F cosine theta is constant, as shown here, the area under the curve represents the work done by the force. So this is where if we were taking university physics, we would start seeing a little bit of integrals being applied here. Basically what an integral is. But this is more in terms of algebra. So here, the displacement between the two is that the D, and the F cosine theta is just as high up as it's going to get. So whatever that cross section is, whatever the shaded area under the curve is, that would be our work. For B down here, a graph of F cosine theta versus D, in which the force varies. The work done for each interval is the area of each strip. Thus, the total area under the curve equals the total work done. So this is just work that isn't constant, that it keeps changing, or F cosine theta keeps changing. So what they did is they distributed in little rectangles. So that way they can get a more precise reading of what the area under the curve actually is. For figure 7.4, network will be simpler to examine if we consider a one-dimensional situation, whereas force is used to accelerate an object in a direction parallel to its initial velocity, such as here. A package on a roller belt is pushed horizontally through a distance d. Net work is done on the box by resolving all of the forces into F net, and this force acts through a distance d. So we have weight pushing down, obviously, normal force pushing up. We have the mass of the box of the package is 30 kilograms. We have force of friction from the right side pushing to the left at 5 newtons. We have the force applied on the left side going to the right at 120 newtons. And the displacement is 0.8 meters. So from there, this is going back to slide 9. We can express our work in those terms. If theta is equal to 0, well, cosine of 0 would be 1. So we can get rid of that cosine theta. So we would get F net d. But we know that force in general equals ma. So we can substitute that ma for our force. So we have mad, mad. If the displacement d equals x minus x naught and v squared equals v naught squared plus 2ad from chapter 2, then we can see that a equals v squared minus v naught squared over 2d. All we're doing is rearranging that second equation to equal its acceleration. So if we know that equals acceleration from that equation, we can go ahead and substitute it back to our work equation over here. Okay. So we have here, we have a displacement on top if we were to multiply it, and a displacement on bottom. So we can go ahead and cancel those out, right? And so that leaves us with a 1/2. The 1/2 comes from the 2 at the bottom. And what we did here is we split up the velocities here. So you have 1/2 mv squared from this part here, and minus a 1/2 mv naught squared. This equation here is our work energy theorem. So from that equation, using the work energy theorem, we assume we can start from rest. So our v naught would be 0. So if we're starting from rest and we know that there's going to be a motion, we can call this equation here, this part here, which you can see here, our kinetic energy equation. So that is giving our energy that is actually in motion. This gives a method of calculating the energy of a transitional motion of an object. Notice that the energy is proportional to velocity squared, so twice the speed is 4 times the energy. So obviously the faster this goes, the greater the energy is going to be, which would make sense. The faster any object is, would produce more energy. So we're going to go back to our figure 7.4 as the example. Suppose a 30 kilogram package on the roller belt conveyor system is moving at 0.5 meters per second. What is the kinetic energy here? All right, that's our work energy theorem, and here we go. So we know that our kinetic energy is 1/2 mv squared. We know that it weighs 30 kilograms. We know that it is going at 0.5 meters per second, and the 1/2 kind of just drops there. So that'll give us 3.75 joules. Pretty straightforward. All right, now calculate the net work done on this package if we're going to go ahead and put everything else in there. The 120 newtons, that is a constant applied force through a distance of 0.8 meters with the friction of 5 newtons. And also, what is the work done by each force, and how do these compare to the net work? Okay, so there's 2 parts we have to work for here. So for A, if we want to find the net work, we need to find the net force first. Well, we know there's a force applied and there's also a friction force. So if we do net forces, if we sum up the forces here, we know that there's a positive 120 and a negative 5. So 120 minus 5 is 115. So if we know it's 115 newtons over a displacement of 0.8, we can go ahead and get our net work. So that would be 92 joules. So for each force that we have, we're going to go ahead and find our work. So this is each individual force. So our force applied, which on the problem says it was 120. We're going to do that. 120 over that 0.8, that would give us 96. And for our friction force, we're going to do the same thing, but only that negative 5. So that'll give us negative 4 joules, which makes sense. If there's friction, you know that you're losing energy there. But you notice that if we're able to add them up, including these two, our gravity and our normal force, these two are 0 because there is no motion in the vertical. So there's no force in the vertical, which means that there's no energy in the vertical, which means there's no work. So if we add them all up, 0, 0, 96, and minus 4, we still get 92 joules, which makes sense because we found the network up here. So all we did here is just break it apart and verify that it would actually be 92 joules. All right, if the package was moving at 0.5 meters per second from example 2, before we pushed it from example 3, then what is the final velocity after the push? So now we're going to go ahead and complete the whole problem here. So if we want the initial, or we have the initial, and we want the final velocity, we can go ahead and solve for it using our work energy theorem. Because we have in our initial, that's 0.5 given from 7.2, from our example 7.2. So we know that's our initial. We want to find our final. So what they do here is they rearrange this formula to just have our v squared on the left side, everything else on the right side. And we know both of these, right? We know it's 92 joules for our net work, and we know our initial kinetic energy, 3.75. So that gives us 95.75 joules. So we'll have to remove this 1/2 from the left side. So you multiply by 2 to get rid of it. And you divide by your mass on the other side. So that's why mass is divided here. And to get rid of the squared, you square root. So once we do all that and plug in all the numbers, you get 2.53 meters per second. That's our final velocity there. All right, if the package was moving at 0.5, like we said in 7.2, before it was pushed at 7.3, then using the final velocity we just found, how far does the package slide down the conveyor, assuming friction is constant, assuming that we are actually using that 5 newtons the whole way. Okay, so now we want to find our displacement. We're using the friction work in this case, right? And we know our work for friction was negative 95.75. We know our friction force is 5, so this equation here came from our original work equation, just W equals FD cosine theta, but theta is 180, so that doesn't count. It gives you a -1, which is why there's a negative here. But there's also a -5, so cancels out the negatives there, which makes sense because there's no way if you're still traveling in a constant speed or a speed in the positive direction, you would get a negative displacement. So you do these divisions here and you get 19.2 meters. That's how far it goes if the friction was constant. Okay, so that's one form of energy. We have our kinetic energy, but we also need to talk about our potential energy. Like I said, everything has some type of energy, so this is more of a stationary energy, I would say. So climbing the stairs and lifting objects is work in both the scientific and everyday sense. Specifically, it is the work done against the gravitational force. When there is work, there is a transformation of energy. The work done against the gravitational force goes into an important form of stored energy that is called potential energy. If the object is lifted straight up at a constant speed, then the force needed to lift it is equal to the weight, mg. The work done by on the mass is then W equals FD. So we have our mg, which is our force here, so we just substitute that, mgh. We define this to be our gravitational potential energy, PEG, put into or gained by the object Earth system. This energy is associated with the state of separation between two objects that attract each other by the gravitational force. For convenience, we refer to this as the PEG gained by the object, recognizing that this energy is stored in the gravitational field of Earth, just for simplicity's sake. Why do we use the word system, though? Potential energy is a property of the system rather than a single object due to its physical position. An object's gravitational potential is due to its position relative to its surroundings within the Earth object system. The force applied to the object is an external force from the outside the system. When it does positive work, it increases the gravitational potential energy of the system. Because gravitational potential energy depends on relative position, we need a reference level at which to set the potential energy to equal 0. We usually choose this point to be Earth's surface, but this point is arbitrary. What is important is the difference in gravitational potential energy, because this difference is what relates to the work being done. An example, the difference in gravitational potential energy of an object in the Earth object system between two rungs of the ladder will be the same for the first two rungs as for the last two rungs. So it really just depends on where you're taking that reference point to be. It's arbitrary. Okay. Gravitational potential energy may be converted to other forms of energy, such as kinetic energy. If we release the mass, gravitational force will do the amount of work equal to mgh on it, thereby increasing its kinetic energy by the same amount, by the work energy theorem. We will find it to be more useful to consider just the conversion PEG to KE, without explicitly considering the intermediate step of work. This shortcut makes it easier to solve problems using energy, if possible, rather than explicitly using forces. More precisely, we define the change in gravitational potential energy, remember that's what the triangle's for, del, PEG, to be change in PEG equals mgh, where for simplicity we denote the change in height by h rather than the usual change in h. Note that h is positive when the final height is greater than the initial height, and vice versa, of course. The equation PEG equals mgh applies for any path that has any change in height, not just when the mass is lifted straight up. It is much easier to calculate mgh, a simple multiplication, than it is to calculate the work done along the complicated path. The idea of gravitational potential energy has the double advantage that it is very broadly applicable, and it makes calculations easier. From now on, we will consider that any change in the vertical position h of a mass m is accompanied by the change in gravitational potential energy, mgh, and we will avoid the equivalent but more difficult task of calculating the work done by and against or against the gravitational force. So it really just matters from start to finish between those two. Anything in between gets really complicated really quick. So for example, 7.6, a 60 kilogram person jumps onto the floor from a height of 3 meters. If he lands stiffly with his knee joints compressing by 0.5 centimeters, calculate the force on the knee joints. All right. So we have our work equals FD cosine. But we know that this is just negative FD, as we said in the previous slide. And we know that there's going to be a change in height. Change in height means gravitational potential energy. So this is why we have our negative mgh. Okay. Negative because he jumps onto the floor, so he is decreasing in height here. So we have our FD equals mgh, right? And we want to know the force on the knee joints. So we're going to solve for force. So we have 60 kilograms, right? That's the 60 kilogram person. 9.8 for G. The height that they dropped, so 3 meters. And the displacement here is going to be the displacement on the knee joints. So 5 centimeters or 5 times 10 to the negative third meters. And that all yields 3.53 times 10 to the fifth newtons. That's how much force is going to be on the knee joints. Okay. So the trick here was to remember that you are talking about energy and you could still use this force equation with our energy. The only reason we could solve this problem here is because we're able to do that. So that's what our final equation came from. All right, conservative forces. Potential energy is the energy of a system has due to position, shape, or configuration. It is stored energy that is completely recoverable. A conservative force is one for which work done by or against it depends only on the starting and ending points of a motion and not the path taken, like we mentioned earlier. We can define a potential energy PE for any conservative force. The work done against a conservative force to reach a final configuration depends on the configuration, not the path followed, and is the potential energy added. Work is done by a force, and some forces, such as weight, have a specific or special characteristics. A conservative force is one, like gravitational force, for which work done by or against it depends only on the starting and ending points of a motion and not the path taken. We define the potential energy PE for any conservative force just as we did for gravitational force. For example, when you wind up a toy, an egg timer, or an old fashioned watch, you do work against the spring and store energy in it. We treat these springs as ideal. There is no friction or thermal energy, just for simplicity's sake. This stored energy is recoverable as work, and it is useful to think of it as potential energy contained in the spring. Indeed, the reason that the spring has this characteristic is that its force is conservative. That is, a conservative force results in stored or potential energy. Gravitational potential energy is one example, as is the energy stored in the spring. We will see how conservative forces are related to conservation of energy. Okay, so now we have potential energy of a spring. Let's obtain an expression for the potential energy stored in a spring, PES. We can calculate the work done to stretch or compress a spring that obeys Hooke's law. Hooke's law states that the magnitude of force F on the spring and the resulting deformation of change in L are proportional, so F equals K change in L. For our spring, we will replace change in L by the distance x, so that the spring is stretched or compressed along its length. So the force needed to stretch the spring has a magnitude of F equals Kx, where K is the spring constant force. The force increases linearly from 0 at the start to Kx in fully stretched position. The average force is Kx over 2, thus the work done in stretching or compressing the spring is work of the spring equals Fd. So that would be Kx divided by 2 times x, which is 1/2 Kx squared. That would be our work done by a spring. Alternatively, we saw that the area under a graph of F versus x is the work done by the force. In panel C, on the next slides, we will see that this area is also 1/2 Kx squared for the linear force on the spring. We therefore define the potential energy of the spring PES to be PES equals 1/2 Kx squared, where K is the spring constant again, and X is this displacement form from its undeformed position. The potential energy represents the work done on the spring and the energy stored in it as a result of stretching or compressing it at distance x. The potential energy of the spring, PES, does not depend on the path taken. It depends only on the stretch or squeeze x in the final configuration, so it describes a conservative force again. So you'll see a repetition of this. Most of the time, unless indicated otherwise, we will have a conservative force. All right, so in this figure, for A, we have an undeformed spring that has no potential energy stored in it because it's not stretched or compressed. For B, the force needed to stretch or compress the spring at distance K has a magnitude of F equals Kx, and the work done or to stretch or compress it has a 1/2 Kx squared. Because the force is conservative, this work is stored as the potential energy. Kes is the spring, and it can be fully recovered. For C, a graph of f versus x has a slope of k, and the area under the graph is 1/2 kx squared. Thus, the work done on the potential energy is 1/2 kx squared. So that brings us to conservation of mechanical energy. What does the work energy theorem take when only conservative forces are involved? The work energy theorem states that the net work force by all forces acting on the system equals its change in kinetic energy. An equation form that means this: the regular 1/2 mv squared minus 1/2 mv naught squared, and that's our potential energy, or our kinetic energy, I'm sorry. If our only conservative forces act, so we have our net work equals our conservative work, where work C is total work done by all conservative forces, that means our conservative work is equal to our change in kinetic energy. Now, if the conservative force, such as gravitational force or a spring force, does work and the system loses potential energy, that is, if our conservative forces is equal to the change in potential energy, negative, therefore our negative potential energy is equal to our change in kinetic energy, or our change in kinetic energy plus our change in potential energy equals 0. This equation means that our total kinetic and potential energy is constant for any process involving only conservative forces, which makes sense. There would be both energies would have to equal 0 if everything is staying constant. That means our energies aren't changing between their transformations. That is, for conservative forces only, we have our Ke plus Pe is constant, and our initial Ke plus our initial Pe is equal to our kinetic energy final plus our potential energy final. So this is known as the conservation of mechanical energy principle. In a system that experiences only conservative forces, there is a potential energy associated with each force, and the energy only changes form between kinetic energy and the various types of potential energy, with the total energy remaining constant. This total energy plus potential energy of the system is defined as the mechanical energy. This means that as long as only conservative forces are involved, all of the energy in the system remains constant, and it's just transferred between kinetic and potential forms. So it means that there's no thermal, there's no other type of energy that can be involved. We're just sticking with our potential and our kinetic. And remember, our potential could be our gravitational potential or our spring potential. Those are the only two that we've talked about at this point. So that brings us to example 7.8. We have a 0.1 kilogram toy car. It is propelled by a compressed spring, as shown above. The car follows a track that rises 0.18 meters above the starting point. The spring is compressed 4 centimeters and has a force constant of 250 newtons per meter. Assuming work done by friction is negligible, find A, how fast the car is going before it starts up the slope, and B, how fast is it going at the top of the slope. So we want to know, here's our starting point and here's our ending point. And we know that we have a spring involved. We know that there's going to be some type of gravitational potential energy involved because we have our H, and there's movement. So we're going to have our kinetic energy involved as well. And with all this, we always have work. Okay, so this might look a little confusing, but we're going to go ahead and start off with our conservative forces. If we have conservative forces, that means our energy is conserved. So that means our initial initial potential equals our final kinetic and final potential. Right? But like I mentioned, we have our kinetic energy here, and our potential energy can be both gravitational or kinetic, or gravitational or spring. And that's the same for both sides. So we have kinetic, gravitational, spring, kinetic, gravitational, spring. Right? So we'll go ahead and zero out what we don't know. We know at the beginning there is no motion. There's absolutely no motion. So there's no kinetic energy at the beginning. We can say that since this distance here is 18 centimeters, we can say that this line on the horizontal is 0. So that means there's no gravitational potential energy either. But we know there's a spring. So on the left side, all that is left is 1/2 kxi squared, our initial spring potential energy. That brings it to the right side. We know that the car is moving at the top. We know that here there is no kinetic or potential, or gravitational potential or spring potential, right? Because remember here it's right before it starts going up the slope. So we're actually talking about this point here. The height hasn't changed yet. There is no spring. The only thing that there is the car is moving at this point. So we only have our kinetic. And we want to find the velocity it's going right before it goes up the slope. So we solve for our v final in this scenario. We rearrange everything. Our 1/2 cancels out. We move over the m and square root it to get rid of the square. So that gives us 2 meters per second. That's how fast it's going right before the slope. Okay, so now we come to the second part. We want to find out how fast it's going at the top of the slope. Well, we're going to go ahead and start here at the very beginning, and now we're going to end over here. So that means we are still moving at the end, and now we have some gravitational potential energy. No spring though, because there is no spring at the very top. On the left side, we still have only spring. So we go ahead and rearrange everything and solve for our v final, plug everything in, and that'll give us 0.687 meters per second. So that's how fast it's going at the very top of the slope. Now, one of these slides did say that there's various ways to find energy. If we wanted to, we could start by saying that this is our beginning point from the very bottom of the slope, and our ending point is at the very top of the slope for part B. Because that would just be like, okay, well, we know that our initial velocity in this case would be the 2 meters per second, and that's all we have. And on the right side, we would still have our 1/2 mv final squared plus mgh final. So it really just depends on where your points are at. Here, to keep it simple, we kept our starting point at the same point, right before the spring launches this toy car. But there is different ways to solve each problem. Right? So we talked about conservative forces. Now we're going to talk about non-conservative forces. So forces are either conservative or non-conservative. A non-conservative force is one for which work depends on the path taken. Friction is a good example of a non-conservative force. Work done against friction depends on the length of the path between the starting and ending points. Because of the dependence on the path, there is no potential energy associated with non-conservative forces. An important characteristic is that work done by a non-conservative force adds or removes mechanical energy from the system. Friction, for example, creates thermal energy that dissipates, removing energy from the system. Furthermore, if the thermal energy is retained or captured, it cannot be fully converted back to work. So it is lost and not recoverable in the sense as well. So, like I was mentioning earlier in this chapter, thermal energy is a very common one. Anything that has friction, anything that has any type of motor, if you've ever been around the motor, you can feel some of the heat coming off of it. I mean, there's thermal energy almost everywhere. So it's one of those very common ones. The amount of the happy face erased depends on the path taken by the eraser between points A and B for non-conservative forces, right? So for A, it's just a straight line. For B, we see more of a M-shaped type of thing. It's kind of a representation of what we were talking about in the last slide. So mechanical energy may not be conserved when non-conservative forces act. For example, when a car is brought to a stop by friction on level ground, it loses kinetic energy, which it's dissipated as thermal energy, reducing its mechanical energy. What form does the work energy theorem take when both conservative and non-conservative forces act? Well, the work done by non-conservative forces equals the change in the mechanical energy of the system. Since the work energy theorem states that the net work on the system equals the change in its kinetic energy, which is net work equals change in kinetic energy, and the net work is the sum of the work by non-conservative forces plus the work by its conservative forces, we get our work done by non-conservative forces plus our conservative forces is going to equal our change in kinetic energy. That's just putting it all together, which makes sense that, okay, well, we have conservative forces that we know are acting, but we also know that there's friction, thermal energy, stuff like that, but that's still incorporated into our kinetic energy in the long run. Okay, so consider a person pushing a crate up a ramp and is opposed by friction. The work done by a conservative force comes from a loss of gravitational potential energy. So our conservative force here would be negative potential change in potential energy. Substituting this equation into a previous equation and solving for our non-conservative forces, we get the conservative force basically, change in Ke plus change in Pe. This equation means that the total kinetic energy changes by exactly the same amount of work done by non-conservative forces. In our example, this is the work done by the person minus the work done by the friction. So even if the energy is not conserved for the system of interest, in this case the crate, we know that the equal amount of work was done to cause the change in total mechanical energy. So basically we know that, okay, well, we have conservative forces, non-conservative forces. If we put all the energies together, they have to equal both, which this equation gives us. Okay, so for example, 7.9, we have consider a baseball player sliding to a stop on level ground using the energy considerations. Calculate the distance the 65 kilogram baseball player slides, given that his initial speed is 6 meters per second and the force of friction against him is a constant 450 newtons. All right. So we have, it shows it here. From here, we have the explanation is friction stops the player by converting his kinetic energy into other forms, including thermal. In the terms of work energy theorem, the work done by friction is negative, is added to the initial kinetic energy to reduce it to zero. The work done by the friction is negative because friction is opposing the direction of the motion, which is theta is equal to 180. So there's a negative 1 there. So our non-conservative forces is negative friction times our displacement. So we have 1/2, which is our 1/2 mvi squared, which is our kinetic friction, kinetic energy, minus our friction, which makes sense. That's going to try to stop it. Okay, so we want to find out how far he gets. What's the distance before he stops applying the friction? So we get this equation here and solve it for D, which is just dividing by F on both sides. So we have 65 kilograms, 6 meters per second times over 2 times 450 newtons. So that means that the baseball player is only going to go 2.6 meters. And that's using the work energy theorem that we looked up before. Right, so now the same baseball player is at an angle of 5 upward a surface similar to that of a baseball stadium. The player slides with the initial speed of 6 meters per second, and the force of friction against him is 6 newtons. Determine how far he slides. Okay, so same scenario, but now we have a displacement. So again, we're going to go ahead and get our work energy theorem going. So here, the only difference is that now we have this mgd sine theta. This happens because, okay, well, if he's at an angle, that means that he's going to go up a certain height, right? So here what they do is they use the Pythagorean theorem and to solve for this component of our displacement. So here we have, he's still moving before, so we have 1/2 mvi squared plus 0 because there is no potential energy at the starting point. And we have our work done by friction, so that's included on the left side, like the example before. And on the right side now we have mgd sine theta because there's obviously going to be some gravitational potential energy that is added to the end because again, he is going up a 5-degree incline, meaning there is going to be some height. But again, all we have to do is solve for our displacement. Here, what you have to do is get your displacement on the same side and then factor it out. So if we were able to add our force D to the right side and then pull it out from both variables, which is why you have your friction plus mg sine theta down here. Okay, so if we're able to do that, we can go ahead and plug in everything. We have 0.565.6 divided by 450 plus 65 times 9.8 sine of 5 degrees. So that gives us 2.31 meters, which is less than what he was going if it was leveled, which was 2.6. So obviously the height or the incline would make a difference. All right, conservation of energy again. Energy, as we have noted, is conserved, making it one of the most important physical quantities in nature. The law of conservation of energy can be stated as follows. Total energy is constant in any process. It may change in the form or be transferred from one system to another, but the total energy remains the same. We have explored some forms of energy and some ways it can be transferred from one system to another. This exploration led to the definition of two major types of energy: mechanical energy, Ke plus Pe, and the energy transferred via work by non-conservative forces. But energy takes many forms, manifesting itself in many different ways. And we need to be able to deal with all of these before we can write down an equation for the above general statement of the conservation of energy. At this point, we will deal with all the forms of energy by lumping them into one single group called the other energy, OE. Then we can state the conservation of energy in the equation as formed. So we have kinetic energy initial, potential energy initial, work of our non-conservative forces, and our other energy initially. So that'll equal our kinetic energy final, potential energy final, and our other energy final. That could be any other energy that is brought into the system. Like I said, most common one is thermal, so the thermal energy that we do find can go in there. So, just so you know, other forms of energy, we have electrical energy is a common form that is converted to many other forms and thus work in a wide range of practical situations. Energy, or electrical energy, is pretty much everywhere. Electrical energy is powering this laptop that I'm recording this lecture in. Fuels such as the gasoline and food can carry chemical energy that can be transferred to a system through oxidation. Chemical fuel can be also produced electrical energy, such as in batteries. Batteries can in turn produce light, which is a very pure form of energy. Most energy sources on Earth are in fact stored energy from the energy we receive from the sun. We sometimes refer to this as radiant energy or electromagnetic radiation, which includes visible light, infrared, and ultraviolet radiation. Nuclear energy comes from processes that convert measurable amounts of mass into energy. Nuclear energy is transformed into the energy of sunlight, into electrical energy in power plants, and into the energy of heat transfer and blast in weapons. And we also have atoms and molecules inside other objects are in random motion. This internal mechanical energy from the random motions is called thermal energy because it is related to temperature of the object. So these are all the other forms of energy that can be converted into one another and can do work. So we are just classifying all of this into other energy for now. Okay, so the transformation of energy from one form into others is happening all the time. The chemical energy in food is converted into thermal energy through metabolism. Light energy is converted into chemical energy through photosynthesis. In a larger example, the chemical energy contained in coal is converted into thermal energy as it burns to turn water into steam in the boiler. This thermal energy in steam is in turn converted to mechanical energy as it spins a turbine, which is connected to a generator to produce the electrical energy. In all of these examples, not all of the initial energy is converted into the forms mentioned. This is important in the next, as this is an important point is discussed next. Another example of energy conversion occurs in a solar cell. Sunlight impinging on the solar cell produces electricity, which in turn can be used to run the electric generator. The energy is converted from the primary source of the solar energy into an electrical energy and then into mechanical energy. So, even though energy is conserved in any energy conversion process, the output is of useful energy of work will be less than the energy input. So, every transformation of energy is less and less and less than the one prior. It doesn't always 100% go into the next stage. So here we just have a simple chart of the efficiency, which is the useful energy or work output divided by the total energy input. That'll just give us a small percentage of what actually transfers, or what can transfer. So for cycling and climbing, we only have a 20%. For swimming to the above the surface is 2%. Swimming submerged is 4%, and so on and so forth. But that brings us to power. Power, the word conjures up many images: a professional football player muscling aside his opponent, a dragster roaring away from the starting line, a volcano blowing its lava into the atmosphere, or a rocket blasting off. These images of power have in common the rapid performance of work, consisting with the scientific definition of power as the rate at which work is done. So, power equals work over time. And our SI unit for its power is going to be the watt, which is a capital W, where 1 watt equals 1 joule per second. So, because work is energy transferred, power is also the rate of energy is expended. A 60-watt light bulb, for example, expends 60 joules of energy per second. Great power means a larger amount of work or energy developed in a short time. For example, when a powerful car accelerates rapidly, it does a large amount of work and consumes a large amount of fuel in that short time. And I'm pretty sure we can all complain about gas prices here and there. So examples of power are limited only by the imagination because there are many types, as there are many forms of work and energy. Sunlight reaching the Earth's surface carries a maximum power of 1.3 kilowatts per square meter. A tiny fraction of this is retained by the Earth over the long term. Our consumption rate of fossil fuels is far greater than the rate at which they are stored, so it is inevitable that they will be depleted. Power implies that energy is transferred, perhaps changing forms. It is never possible to change one form completely into another form without losing some of its thermal energy. For example, the 60-watt incandescent bulb converts only 5 watts of electrical power to light, with 55 dissipating to thermal energy. Furthermore, the typical electrical power plant converts only 35 to 40% of its fuel into electricity. The remainder becomes a huge amount of thermal energy that must be dispersed as heat transfer as rapidly as it is created. A coal-fired power plant may produce 1,000 megawatts. 1 megawatt is 10 to the 6 watts of electrical power. But the power plant consumes chemical energy at a rate of 25 megawatts, creating the heat transfer to the surroundings at a rate of 15 megawatts. So, not all transitions of energy is actually transferred to the next one, as you can clearly see here. That brings us to 7.11 example. What is the power output of a 60 kilogram woman who runs up a 3-meter flight of stairs in 3.5 seconds, starting from rest and having a final speed of 2 meters? Okay, so we have a lot from the very beginning. We have 60 kilograms, so we have mass. 3 meters, so we have a height. We have a time, 3.5 seconds. We have an initial velocity of 0 and a final velocity of 2 meters per second. That's a lot to take in, but we do know that energy revolves around mass, velocity. We have two velocities here, so we can use our work energy theorem. And we also know that a time, well, then if we're looking for power, we definitely need a time. So we'd have that. So we can easily just use our work energy theorem from the top for substituting for work, and we have our time. So we can just go ahead and plug in everything. Okay, so moving from rest at the beginning, right? So no energy, no kinetic energy. And we're going to say our height was 0, so no potential energy. So anything on the initial side is 0. At the end, we know that we are moving with a velocity of, 2 meters per second. And we know we have a height of 3 meters. So we have our V final here and our potential. That goes at the very top. Plug in everything there. And our time, so once we do all that, we get 538 watts. How much power she uses to go up the flight of stairs. Okay, so energy consumption and your electricity bill. We usually have to pay for the energy we use. It is interesting and easy to estimate the cost of energy for an electrical appliance if its power consumption rate and time used are known. The higher the power consumption rate and the longer the appliance is used, the greater the cost of the appliance. The power consumption rate is P, which is power equals work over time, which would be our E, which here is energy supplied by the electricity company. That would be our work done. And we know that if we can manipulate that, we're going to have our power times time, which is what we're trying to find out. Electricity bills state that the energy used in units of kilowatt per hours, which is the product of power in kilowatts and time in hours. The unit is convenient because the electrical power consumption at the kilowatt level for hours at a time is typical. So here we have the energy consumed by humans is converted to work, thermal energy, and stored fat. By far, the largest fraction goes to thermal energy, although the fraction varies depending on the type of physical activity. But it's just another conversion of the energy and the power that can be transferred. So you see that our other energy comes from our food energy. That could be chemical energy, thermal energy, so forth. That gets transferred between these three, even though most of it still goes to thermal energy anyway. So if a person who normally requires an average of 12,000 kilojoules, which is around 3,000 kilocalories of food energy per day, consumes 13,000 kilojoules per day, he will steadily gain weight. How much bicycling, which is about 400 watts of a moderate speed, that's our power, per day is required to work off this extra 1,000 kilojoules. You see, physics is basically in everything here. Okay. So here we have our time, energy over our power, but we know that we're using the energy, which is 1,000 kilojoules that we're trying to get rid of, and using it by bicycling, 400 watts. That'll take about 2,500 seconds, which is about 42 minutes. So if we're trying to convert that here, 1,000 kilojoules is this is a straight conversion factor. 1 gram of fat is divided by 39 kilojoules. That's a conversion factor. So we're trying to get rid of 1,000 kilojoules. We need to. That'll give us 26 grams, assuming that energy constant of fat is to be 39 kilojoules per gram. So this workout would have to be 42 minutes every single day, so they would not gain any of that extra weight from that 1,000 kilojoules. So here we just have another chart representing where all the different types of energy goes, world energy consumption by source in billions of kilowatts. This is dated back in 2006. So we see that petroleum is about 35.43%. The next one is coal. So that's our fossil fuels. We have dry natural gas coming in third. hydroelectricity, or dams, nuclear electricity, or nuclear power plants, geothermal, wind, solar, biomass, which should probably be bigger by now, and that's using electricity, and this is not using electricity. So hopefully this is a little bit well-rounded now, being 14 years later. So we have our world energy consumption. It is steadily going over. Um, this is back in 2011, so around here. After everything after this is just projected. Past and projected world energy used, based off a 2011 article. So you can see here that every year that goes by, the world using more and more and more energy, which makes sense. The world's being populated a lot faster, so more things are being ran and used, so more energy is being used. And this last one is just the power consumption per capita versus GDP per capita for various countries. Note the increased energy usage with increase of GDP. Back in 2007, so you see a lot of countries down here. They don't use a lot of energy here, and you keep going up here, you see more of the powerful countries around the world, and then you see us way over here. So, go ahead and go over this chapter 7 on work energy. Like I said, a lot of this stuff can be used in the previous chapters, like chapter 2, chapter 3, even chapter 4. Chapter 4 is pretty much involved in here anyway, because we're talking about forces. So go ahead, make sure you brush up on your forces. Make sure forces always equals ma. That's always your given equation that you can pretty much put anywhere in this chapter. So go ahead and review this, and hopefully that gives you a better understanding of chapter 7.